So welcome to the trabajo fin de master defense of Miquel Duran Pou. The jury will be Massimiliano Zanin as vocal, as secretary, David Sanchez as vocal, and myself, Juan Fernandez Gracia, as the president. And you'll have 20 minutes, 25 minutes to give talk about to defend your work, and after that we'll make some questions. So the floor is yours.
Okay, thank you. Yes. Okay, in my thesis, I propose a model to capture asymmetric language shift in bilingual communities. The motivation for this is my experience as an American citizen when observing linguistic interaction between the inhabitants of the island, which appears to show an asymmetry in terms of the susceptibility of speakers to switch in to one language or the other when spoken to them. In this case, Catalan speakers would be more susceptible to switching to Spanish when spoken to them than the other way around. In order to model this, what I did is to make a modification upon the Abrams-Strokes model, which is a language composition model that uses two parameters to define the transition probabilities from one state to another. These states here represent language use. Here it would be language A and language B. And the two parameters are the prestige S, which is a language preference model that introduces bias to the system. In this case, for the prestige goes from 0 to 1. So for a prestige higher than 0.1, this will make the transition from B to A preferable, making the language A the prestigious one. And then we have the volatility, which is a positive exponent on the variable that introduces a nonlinear effect. This variable, X, is the proportion of neighboring speakers of language A. But in the mean field limit, which is where we're going to be most of the presentation, the number of speakers tends to infinity and they become fully connected. So the variable X becomes the normalized density of speakers being a continuous variable. So we can define the model using a single ordinary differential equation, since the density of speakers of language B will be 1 minus X. So, the modification performed upon this model is basically splitting the volatility parameter into two different ones. So the population speaking language A will have one volatility, alpha 1, and the other will have alpha 2. So the alpha 2 will affect the transition to A and alpha 1 to B. So for example, for prestige higher than S equals 0.5, will mean that the population with volatility alpha 1 will be speaking the prestigious language. And this is how the equation stands. But however, in order to, for clarity, we do a coordinate transformation of the volatility parameters. So we use, instead of alpha 1 and alpha 2, we use the mean volatility, which we call alpha, and the difference between the volatilities. This way, setting delta to 0, we recover the Abrams-Strokes model. Also, this system has a symmetry, so we will only explore delta higher than 0, since delta lower than 0, we can extrapolate the results. And this will mean that alpha 2 will always be greater than alpha 1. So this is the equation of our model. Now, solving this, we can find two trivial solutions, which are x equals 0 and x equals 1. But in order to find other solutions, we must solve a transcendental equation, which we cannot do analytically. So I tried several methods to approach the exact solutions analytically, to no avail. So we will try to find other ways to study these non-trivial solutions. But first, let me show you the phase space of this model, which is the main result of the thesis, where we find two novel phases that we didn't see in the Abrams-Strogatz model, which here we have the phase space. I don't. Okay. It's okay. I think it still works. Yeah. Okay. In the Abrams-Strogatz model, we find only two phases: coexistence, or bistability of existence, or dominance, and with the transition at alpha equals 1. What we see when we increase delta is that a central region opens up from alpha equals 1 with two novel phases. One being the dominance of B, which means that the stable solution is only x equals 0. And then if the prestige is high enough, we have the possibility of a stable coexistence state, giving us a bistable phase between coexistence and extinction that will have some nuances that we'll explore later. Complementarily, we have the dependence on delta for slices of S, and we see that at delta equals 0, we have only the two phases of the Abrams-Strogatz model. But as we increase delta, the central region opens up with its width being equal to delta. This region is of no interest because it means that alpha 1 is lower than 0, which cannot be because the volatility is a positive exponent. Okay, but before going into the stability analysis, we can take a qualitative approach to these new central regions with the two novel phases. And what we do is construct a potential that will show us the stable states with the minima and the unstable states in its maxima. And what we see at delta equals 0 is the biased Abrams-Strogatz model with, I used S equal 2/3. So we have coexistence states up until alpha equals 1, and above that we have a bistability between existence or extinctions of the two languages with an unstable fixed point between them. And as we increase delta, we find this new phase of bistability, since we have a coexistence state as well as a stable fixed point in the trivial solution. And as delta increases further, we see that these two non-trivial solutions, one stable and one unstable, will collide and disappear, giving us the other novel phase, which is only dominance of B. So language A, nobody speaks language A, x equals 0. Here, yeah, well. Now, having seen this qualitative first step, we can go to the stability analysis. And we do that by introducing a small positive perturbation in the trivial fixed points, in the trivial solutions. So we can study the time evolution of this perturbation in the limit of epsilon going to 0. Epsilon is the perturbation. So if the perturbation increases, the fixed point will be unstable and otherwise stable. And we find that at x equal 1, the solution is stable for alpha lower than 1 plus delta over 2 and unstable otherwise. And at x equals 0 is unstable when alpha is lower than 1 minus delta over 2 and stable otherwise. Here we have the solutions of the Abrams-Strogatz model, which can be found exactly. And we see that in the trivial solutions change stability at alpha equals 1, which makes sense since this is for delta equals 0. But then as we increase delta, we can infer that the change in stability of x equals 1 will go higher in alpha, and x equals 0, lower in alpha. So we find that for s lower than 0.5, which is the purple, the two branches, which are the non-trivial solutions that we haven't found yet, will move apart from each other, creating this central region with the dominance of B, since we'll only have a stable solution here. And for delta higher than 0.5, the two branches will overlap, creating the B stability with coexistence, since we will have one non-trivial solution that is stable, and still the trivial solution down here that is still stable. But since we cannot solve this analytically, what we can do is to focus on the points where some exponent on the transcendental equation cancels. So we can solve it analytically. And we find that these points are alpha equals 1 plus delta over 2 and 1 minus delta over 2, which are coincidentally the changes in stability of the trivial solutions, where we find only one solution in each. And then we have alpha equals 1, where we find two solutions or none, depending on the prestige, where again it shows us the transition between the two noble phases, since we go from two non-trivial solutions to none. For example, here they collide and disappear. Well, with all this new information, we can now see how we obtained the phase space, where we see the changes in stability of the trivial solutions mark this transition between the regions. This means that the central region is when one population is volatile and the other is not. And then the transition between the two noble phases is marked by the collision of the two non-trivial solutions. Here there are some more values of delta, and that's it. Now we have been in the mean field limit, but we should explore the model in a finite size system to see if there are some absorbing states, and therefore study the lifetime of those that aren't. And what we find when translating the model into an agent-based model, what we find is that there are only two absorbing states, x equals 0 and x equals 1. And so the stable coexistence states found in the mean field limit will be metastable states, and given some time will divert to one of the two absorbing states. And what we expect to find is a dependence, an exponential dependence on the system size, but also on the potential barriers that the system must overcome to reach from the metastable state to the absorbing state. And we find that indeed this is a linear fit with a logarithmic scale. So we find this exponential dependence on n, but also the slope it corresponds to the height of the potential barrier that the system must overcome. Here I simulated 3 of the cases we saw on the potential. So for example, the orange one is alpha equals 0.8 and delta equals 0.5, which is this one. And we see that the potential barrier to get to the closest absorbing state is quite high compared to the other two, which are alpha equals 1.2 and delta equals 1, which is much lower, and alpha equals 0.8 and delta equals 1 is also much lower in order to reach the absorbing state. Also, which state the probability of reaching one state or the other depends on the potential, since first an interpretation of what's going on here is that for a small system size, the fluctuation will be large. So it's easy for the system to quickly get to the closest absorbing state. But as we increase the system size, the fluctuation becomes smaller. So the system has more time to explore the Bayesian of abstraction. And this also is how we can explain to which state to which absorbing state the system goes. Since, for example, in this case, which was the orange one, the state x equals 0 is much further and with a much higher potential value than x equals 1. However, we see that, so it will always end up at x equals 1. And if delta x equals 1, we see this change that in order to reach x equals 1, we have a much larger potential barrier, but the potential barrier to get to x equals 0 is much smaller. So in this case, we see that the system always ends up at x equals 1 statistically. And in this case, it almost always ends up at x equals 0. Now, for the case of alpha equals 1.2, we see that the two potential barriers are quite similar. So for large fluctuations, the system almost always ends up to the closest one, but with smaller fluctuations, we have this more time to explore the Bayesian, and sometimes it will get to the other side and end up at x equals 0. So we see that this is the probability, well, the proportion of times that the system ends up at x equals 1. So as we increase the system size, this proportion goes down. So we have more, like half the time it ends up at one state or the other. As a final note, in the nuances of the new region, we see that the system presents some sort of memory or hysteresis, since the consequences of changes in the parameters depend on when these are applied. This is a consequence of the bistability between a coexistent state and a dominant state. This could be very useful when trying to apply linguistic policies if the results of this model were to be considered, since what I said, changing the parameter at one point or another in the state of the system will lead to very different results. So to summarize, I have proposed a new take on social dynamics in bilingual communities with novel results in regards to language competition models, which can be a first step into studying this asymmetrical switching in language use. And also, this model could be used not only for two different languages, but also with two different dialects or registers as well. Apart from this, we could dive deeper into this asymmetrical switching. And one of the main things is that there are different ways to capture asymmetrical language shift in bilingual communities. What I did is the simplest way, but might not be the optimal, since I just used different volatility in each of the transitions. But this means that when a speaker changes state, their volatility also changes. So maybe it would be interesting to try to construct two different populations with fixed volatilities and allow for the system, well, in each of the communities, for there to be speakers in both states. But also there are other models that use other ways to represent the preference of bilinguals to using one language or the other. For example, without using nonlinear effects. This could also be interesting. And moreover, we could just add complexity to this model to see how realistic it can get by diving deeper into the agent-based model, since we only saw the finite size effects to study the lifetime of the metastable states. And also we could add spatial dependence or compare it to real life data and see if the states provided by the model are able to represent real life situations. This is it. Thank you for your attention, and I will answer any questions. Thank you.
Thank you. So we'll start with David. We stop the recording? No? Yes. Okay.